Uh, One of the few paddlefish talks, so there might be a little bit of repetitive life history stuff, but you guys might have missed the earlier one this morning. Paddlefish are a large, open water, mid-water planktivore, pretty extensive range, Mississippi and Missouri River drainages, ranging all the way from Montana down to the Gulf of Mexico and over to New York State. In Oklahoma, they're fairly abundant in the eastern half of the state, and they live in our reservoirs and rivers. The study area we're talking about today pretty much encompasses the northeast and southeast corner of Kansas and Oklahoma. Some basic life history stuff. They do migrate upstream to spawn. They're strictly freshwater. They require specific hydrological cues, temperatures, and particular substrate, typically clean cobble or gravel. They, at least in Oklahoma, they are capable of spawning annually, but their recruitment is limited based on those hydrological factors, so they exhibit a boom and bust phenomenon where they have large cohorts some years and then no recruitment in other years. Like many of these species, declines are attributed to overfishing and habitat loss or modification. In Oklahoma, it doesn't seem very prominent. They're ranked 14th most popular fish to anglers, yet they're very important because we have a destination fishery in northeast Oklahoma. We have a lot of people coming to Oklahoma to catch paddlefish. So it's a big research and conservation focus for our state, and sort of our basic philosophy is that we put a lot of focus on wild recruitment, specifically in the northeast part of our state. So our study objectives here, playing off of that need for information on wild recruitment, we wanted to use consumer-grade sonar to identify and quantify available substrate types in the headwater rivers of one of our most prominent reservoirs. And through that quantification, we wanted to sort of simulate availability of habitat within those changing hydrology in springtime. So we're taking what we know about the life history of the species, and we're doing a little bit of research on the habitat, and hopefully learning something and using that information to fine-tune our regulatory and conservation actions. So here's a glimpse at the watersheds we're talking about here. This is northeast Oklahoma, southeast Kansas, and although Grand Lake looks like a small lake, it's actually the third largest reservoir in Oklahoma. So the Neosho River is the primary headwater river, and the Spring River is smaller there. And you can see we've got quite a few dams in the system, 15 total on the Neosho River and 2 on the Spring River, and most of those are low head or overflow dams. This study centered around the shaded area there, which includes 108 kilometers of water, 62 kilometers of the Neosho River and 36 of the Spring River. And the northern boundary of each of those rivers is a low head dam at Chetopa and Baxter Springs. And those are barriers for fish. I'd also like to point out that in the Spring River, from the Kansas state line down to the confluence, we have put in a legal restriction. We call this a paddlefish sanctuary. So there is no fishing or harvest of paddlefish allowed in the Spring River. So this information on habitat and recruitment is relevant to us because we're protecting a river, and whether or not it has recruitment value is still really to be determined. So as I was implying, we have, kind of boom and bust recruitment. We also have sort of flashy hydrology in both of these headwater rivers. So here's just a back-to-back year example. In 2014, we saw drought and recruitment failure. We actually saw 0 spawned out fish in the harvest, which is unprecedented for us. But then the following year, we saw a recruitment explosion where we had lots of flooding. And as you can see, just the climbing hydrograph there, lots of great spawning, lots of recruitment. In fact, anglers in 2016 couldn't help snagging 1-foot-long paddlefish, as you see in the picture here. So pertinent to this project, we're looking at how those changes in hydrology are wetting the gravel shoals we see in the picture there, making habitat available for that recruitment. So of course, sonar mapping is not a new technology. It's been used for a long time. Those of you that went to the workshop yesterday got a first-hand experience with this. Primarily, it's been used for classifying submerged habitat. In the picture here, they're looking at deadhead logs. But of course, it follows if you can identify a log, you can probably identify a large fish. So researchers are now using this as kind of a surrogate for abundance estimation. And for this project, we're simply concerned with habitat substrate types. So we weren't actually using side scan sonar as you see here, we were using down scan. And although those pictures generated on the previous slide were using hummingbird technology, which is available to anyone by going to Bass Pro, we were using Lowrance, which integrates well with a company called BioBase. It's a cloud-based service where you can go out and store sonar logs with your consumer grade unit and you upload them to the cloud, and they do a lot of the algorithms, kriging, and they generate basically an output that you can put in GIS, which is a grid with geo-referenced depth and an index of bottom hardness. And so that's what we were interested in here, how the relationship between bottom hardness and depth, which we could then, through simulations, fluctuate and learn something about how habitat is available. To add to the actual sonar data, of course, we had to do ground truthing. So we went out with a substrate sampler, as you see in the picture there, and when waters were extremely low, we went out on foot and visually identified some of these substrates. So then we could back relate those to the sonar data saying hardness index, and we classified our substrate as all the types listed here: detritus, silt, mud, sand, 3 types of cobble, and bedrock. And of course, we were interested mostly in those cobble and bedrock substrates, which are presumed as most valuable for paddlefish spawning. So through our sonar and our ground truthing, we were able to identify what we labeled as spawning habitat. And of course, we generated lots of data, and we found, of course, that that depth and bottom hardness were correlated, where you find harder substrates at shallower depth because sediments settle in the waters that are deepest and wetted year-round. Combining our ground truthing and sonar data, the conclusion we came to here was that any hardness index values above 0.386 we determined to be, quote, spawning substrates. Now again, this is a surrogate for actually going out and taking substrate measurements. So, and of course these gravel shoals, like I showed you in that photo, largely comprise much of the spawning habitat. It's found in the shallower depths, and it is actually out of the water during low river stages. If you know anything about paddlefish, you might say, well, why is sand included there in the spawning substrates? Well, it's simply the fact that it's so rare in our system here that we weren't wanting to sort of exclude it from the upper boundary of what is spawning habitat. We moved on to quantifying habitat within each river. Each river was broken up into 10-kilometer segments just for convenience factor, and so we could sort of demonstrate gradients in habitat availability here. We did find that most of our spawning habitat, cobble substrates, were found in the upper reaches of the river. This is below that first barrier to fish, of course. And although the Spring River provided more habitat, sort of closer proximity to the reservoir where fish are staging for spawning and spending most of their life year-round, there was more relative habitat available within the Neosho River. And so I'm going to talk additionally about sort of a comparison of the two rivers and how we feel that the Neosho is most likely more valuable for paddlefish recruitment. It's also notable that we had a higher density of spawning habitat in the Spring River than in the Neosho River. And whether or not that's important to the fish, we're not real sure yet. So the next major step in this project was actually simulating changes in hydrology and how the habitat becomes available or is lost due to the rise and fall of the springtime flows. So we were able to simulate it over a range of 3.5 meters. And of course we had to simultaneously model gauge height and discharge, because the USGS gauges give us both of those, and we wanted to be able to use either to determine what the habitat availability was. In order to take the next step of how much is available, we had to figure out what's the total amount available, the way we could determine the proportional habitat availability at varying river stages. So we had to kind of use our model to determine what's the total amount of spawning habitat available in the river. So to do that, this figure represents the simulated amount of spawning habitat available, hectares, at different simulated gauge heights. So we actually measured at the upper bounds of each of those trends there, and then we back calculated, simulated what happens when the water goes down, how much habitat's available. So this is a quadratic regression model, and if we project it to its asymptote, that would represent an estimation of what is the max amount of habitat available in each river. And we did that with a little bit of caution, because generally we don't like to project a model that far forward, but it was reasonable that each of those projections fell within the flood stage of each river. So the gauge height, where the maximum amount of habitat was available, was within a reasonable number. So this is the resulting kind of predictive model we come up here, where we can say what is river discharge for each river and how much proportional habitat is available with simulated changes in river discharge for each river. And on the inset there, what I'm sort of showing you there with those vertical dotted lines is the average or median discharge for 2015 and 2016. So that's kind of like an indication of what the normal condition is for each river, where the Neosho has 78% of habitat available and the Spring River has 66%. So just to kind of demonstrate what we're trying to show here is a little river cross section below, where the spawning habitat is represented by the gravel shoal indicated. And so at low river stages, none of that is underwater, so we have zero habitat available. With the rising river, we have proportional habitat availability of 50%. Fish can get to some of the habitat, and then it follows reasonably that once it's all underwater, you're at 100% habitat availability, but you still may be able to accommodate more river flow, which may or may not allow for enhanced recruitment. So here I'm just going to kind of give you a little bit of review or a tail of the tape for the two rivers that we looked at. Some of this we knew going into the project. Neosho River, obviously a farther distance to that first barrier than the Spring River. So we would kind of think that's valuable to the fish. They can migrate a longer distance. Also has a much larger watershed. So that can accumulate a lot more springtime rainfall, potentially result in higher hydrological events. But contrary to that, we saw in 2015 and 2016, the average flow in the Spring River was higher. So these fish are positively rheotactic, so they're opportunistic. If given a choice of one river or the other, they're typically going to go where the flow is greater. So is this of benefit to them to go in the Spring River despite the pluses we see with the Neosho? But a couple concepts this project brings into, as far as proportional habitat availability, we actually saw that for, say, a benchmark where 75% proportional habitat availability for each river, it actually takes 5 times as much water in the Spring River to match the amount of habitat available in the Neosho River. So that's pretty substantial. I mean, that takes a pretty big hydrological event in order for the Spring River to equal that of the Neosho. And sort of along the same lines, I wanted to kind of look at, okay, relative to flood condition in each river, where do we maximize the habitat availability there? Because we're also concerned with anglers and them being able to fish these stocks. So we're getting pretty close to flood stage in the Spring River before all of our habitat is underwater. So we kind of want to find a magic area there where we've got good recruitment due to habitat availability, but we've also got access for anglers to fish the stock. because that's largely how we get our data. So we kind of took it a next step, and this is only preliminary. I'm going to look at lots of other years, but here's an example of 3 years where 2 of which we had recruitment booms in 1999 and 2015, which I referenced earlier, and then 2014 where we had that drought and no evidence of spawning whatsoever. So looking at proportional habitat availability, it's pretty obvious in 1999, a third of what we'd call the spawning season, we had all of the habitat was available in the Neosho River. Spring River, a little less available, but pretty good hydrology. In stark contrast to 2014, we had very little habitat available due to low water. So it just kind of shows you how these concepts work together with actual recruitment, potentially demonstrating some utility to this work. Now in 2015 we have something kind of intermediate, but the commonality here is that Spring River and Neosho River, late in the season, we had high habitat availability in each river, and we did see that we had a high recruitment. So just a couple more slides on the conclusions here. At least all the preliminary evidence here suggests that the Neosho River, of the 2 rivers, probably is more valuable for recruitment. We have a lot more habitat. We have a higher likelihood of inundation of that habitat at lower discharges, and we do have a greater distance. So these, once hatched, these larvae can drift a little bit farther before they hit Grand Lake and potentially settle out into all that silt. One issue with this is, though, there's published evidence demonstrating a loss of spawning gravel in the Neosho River due to all of those low-head dams. So this may be a resource that's kind of going away over time, so that's something we're a little bit concerned about, and we're potentially going to look at this in a little more depth. Also, this kind of brings us back to the whole question of that Spring River sanctuary where harvest and snagging is not allowed. Is that doing anything for the stock? Well, we can't necessarily answer that question with this project alone, but we have some follow-up research that we're going to do where we actually look at recruitment contribution from fish from each river. We're going to use dentary bone microchemistry. It's kind of an interesting technique that has been recently done in paddlefish, and we hope that it has utility for us as well. So this is not the end. This is just one step along the way. So I appreciate your time, and if there's any questions, I'd also like to thank my co-authors and participants in this project. So any questions?